Hello, everybody. My name is Maddie, and currently I'm a first year PhD student in the Department of Materials Science and Engineering at Penn State University. Today I'm going to talk to you about reciprocal space, which is a solid state physics or solid state materials tool that forms our foundation of our understanding of certain material properties. Before I start, I do want to say that while I will be referring to this concept as reciprocal space throughout this presentation, there are several other names that reciprocal space can go by. So this includes K-space, momentum space, Fourier space, frequency space, or inverse space, plus probably some others that I just haven't seen before. So I'm going to start off by talking about what reciprocal space actually is. And to do so, I have to kind of back up and talk about how we define crystal structure in real space. So in order to define crystal structure, we need to define the locations of atoms. In this case, we will set up our lattice, which is our set of points, define our unit cells, and we can then lay atoms on top of that lattice. And then we can kind of describe their position in space that way. It's important to note that within the material there are electrons and other types of particles that can be seen as waves. And an important aspect or feature of waves is this wave vector, which describes the direction in which the wave is traveling. Now, here's where reciprocal space comes in, because reciprocal space is a way to kind of describe these waves. Reciprocal space is defined as the set of k values for which the wave has the same periodicity as the real space lattice. Reciprocal space, or k space, has to do with the momentum of particles within the lattice. You may be thinking at this point, why use reciprocal space? Why bother converting from real space to reciprocal space when we can already define where the atoms are within the crystal? And to do so, we need to kind of talk about the different types of questions that we can ask as physicists or as material scientists. And the first have to do with the real space representation. And this has like a very particle heavy focus. So this can be like, okay, where are the atoms? Can we map out electron density? What are the atoms and electrons' velocities? That sort of thing. However, there are a variety of material properties that we want to know more about that we can't exactly get just from looking at individual atoms and particles. So this can be things like, okay, what are the energies? What are the momentums? Can we map out things like band structure? And then this also kind of plays into our connection to quantum mechanics with wave functions and looking at particles as waves rather than particles. So now I'm going to talk about what exactly reciprocal space looks like. And we have good news here is that it looks essentially the same as real space. The only difference is we have our unit cell has different dimensions in real space versus reciprocal space. So in real space, if we have a lattice parameter of A, in reciprocal space, we would have a unit cell that has a side length of 2 pi over A. But whenever we're talking about our unit vectors, so like our x hat, y hat, and z hat that define our directions in space, those are the same between real space and reciprocal space. Also, for this presentation, I'm going to follow a two-dimensional lattice that has like a simple cubic structure, but like the two-dimensional version of that, just for simplicity, to kind of build up these concepts. Where real space and reciprocal space differ is how we treat different translation vectors. So, as we know, even if we have a primitive unit cell, we can have several different ways of defining those translation vectors that define the unit cell. So like the first could be that we have these two perpendicular A1 and A2 translation vectors. We can also have them be at an angle with respect to one another, like A1 and A2. And the ones in blue here, or there are several different options. Basically, we are not unique is what I'm trying to say. Now, in all three of these examples, we do need an A3 vector, which I define just to be z hat here, or coming out of the page. This is just so that the math works out so that we can easily transform between real space and reciprocal space. And it turns out that we have nice and easy formulas to be able to convert between real space and reciprocal space, which are shown here on the screen. We can do that using a cross product, dividing by the volume of the unit cell. So then whenever we convert these three sets of translation vectors to reciprocal space, we get the following. So for the first set, we have that there's no change in the directions of B1 and B2, just a change in the magnitude from A to 2 pi over A. And then with the second two, we do get some direction change that is determined according to the formulas on the previous slide. It's also important to note that we have this property here between the real space and the reciprocal space vectors that's set up by the Kronecker delta. So, for example, if we take B1 and A1, B1 and project it onto A1, then we should get 2 pi, but if we project B1 onto A2, we should get 0. While we could then use these new translation vectors in our reciprocal space to try to describe things like location of specific atoms within the crystal, the more important use of converting to reciprocal space is actually in diffraction. So whenever we're using real space, real space is very good at looking at individual atoms, versus reciprocal space is better for looking at different planes of atoms, and it can be used to very clearly explain X-ray diffraction. So in order to start exploring the connection of reciprocal space and diffraction, let's consider that we have a certain set of planes within our crystal. So we can see on the left here in reciprocal space is what a series of parallel planes in the crystal would look like. Well, it turns out that if we draw a vector that is perpendicular to this set of planes, that is actually what our vector is in reciprocal space that describes this set of planes. So you can almost think of this as a vector called G, which describes the momentum of the lattice itself, which is a little bit of a tricky concept, but it comes and works out pretty nicely whenever we want to think about things like X-ray diffraction. So it turns out that G has a magnitude of 2 pi divided by D, which is the distance, the spacing between the planes within the crystal. So from here, we're going to investigate what happens whenever we send X-rays toward our sample or our planes of atoms. So here I just have the planes of atoms displayed again with their corresponding G vector. So what happens whenever we do X-ray diffraction is we send an incoming X-ray toward the sample. So we'll call this X-ray Ki. It has a wave vector of Ki. And this gets reflected, and we'll call the reflected X-ray Kf. So it turns out that we get Bragg diffraction when delta K, or the difference in these momenta of the reflected and the incoming X-ray, is equal to that G vector. And it turns out that if you work out the math, this corresponds with the common form of Bragg's law that I'm sure all of us are familiar with. We can also talk about diffraction in terms of Brillouin zones. So this is similar to the Wigner-Seitz cell representation that we use in real space. Same thing is done in reciprocal space. So these blue lines that I have drawn in here on top of our lattice form our Bragg planes for a simple cubic cell, or again, simple square, I suppose, the 2D version of that. And then the first Brillouin zone is in the middle, highlighted in red, followed by the second Brillouin zone, which is broken up into 4 triangles, highlighted in green, and the third Brillouin zone, highlighted in the orange triangles, and there are 8 of those triangles. And this can continue on to have more and more Brillouin zones as well. And it turns out here that the connection to diffraction is that whenever our K vectors of our X-rays lie on the boundaries of the Brillouin zones, that's when we get our diffraction. In addition to looking at Bragg diffraction, we can also tie this idea of reciprocal space to other material properties, such as things like conductivity. In order to do so, we need to talk about how states are filled within a material. So it turns out that within a material, there are only certain allowed K values that our electrons can have. Additionally, we know that by the exclusion principle, there must only be one electron in each state. Because of spin, we can actually have two electrons in each of these K states, which are represented here by a dot in our K space or our reciprocal space. Whenever we talk about which K states are filled, we assume that electrons will occupy the lowest possible energy states first. So this means that it will be useful for us to think about filling up our K states, starting from the middle and working our way outward in a circular pattern. And we will fill up until we run out of electrons in our material. So the size of what we're going to call the Fermi surface, or in this case a Fermi circle, will be dependent on how many electrons there are within the material that you're looking at. And this Fermi surface is a surface such that all states inside the surface are filled with electrons and the states outside of the surface are empty. We can tie this to several different properties, but the property that I'm going to focus on today is conductivity and how electrons are conducted. So whenever we think about electrons flowing, we typically apply a voltage, and whenever we apply this potential difference or an electric field across a material, this actually shifts the location of the Fermi surface. So here we're shifting it a little bit to the left, and in response, the electrons that are now excluded from our Fermi surface. All of the electrons shift so that they're all included in the Fermi surface. And the shifting of those electrons is the moving or conduction of those electrons. In this presentation, I also wanted to mention that reciprocal space has applications in several other fields than material science. While, physicists in material science use reciprocal space as a crucial tool for understanding material properties, there are several other applications, one of them being an MRI technology. And whenever you perform an MRI, the data that is collected from the MRI is actually K-space data, which then has to be reconstructed back into real space or image space to form the image that technicians see whenever they perform an MRI. So reciprocal space is very important for several different fields. So again, I'd like to reiterate that reciprocal space really is everywhere. It helps us to explain different things like diffraction, band structure, electrical properties, or even imaging techniques like MRI, plus many more things that I haven't had the chance to talk about in this presentation. So I hope this video was successful in helping you to better understand reciprocal space, what it is, and why it is so important for the fields of physics and materials science. Thank you.